This video specifically addresses the divisibility rules for prime numbers from 2 through 11. Okay, and if we got some big number that you need to determine what it's divisible by, one technique is to get the prime factorization of that number. The sieve of Eratosthenes can be used to determine what prime numbers are, and here's a table from 2 to 100. What the sieve does is it says, well, I'm going to start with the smallest prime number and cross out all the ones that are divisible by 2. So that would mean anything which is even would be crossed out. I'll just cross out all these columns right here. Then you move to the next prime number and divide, which is 3, and divide anything, cross out any number that's divisible by 3. And I can see 21 is divisible by 3, and 51 is, and so on. Okay, and then you go to 5, 7, and so on. And when you're done doing that, this is what you get for the prime numbers between 2 and 100. Okay, those are the prime numbers. Now on this board, we're going to look at this huge number here and decide how to do the prime factorization. I've listed the first few prime numbers here, 2, 3, 5, 7, 11. Of course, there are infinitely many prime numbers. But here's a suggested technique. Start with the number that you want to get the prime factorization for, and start dividing by the smallest prime number that goes into it evenly, in this case 2. How do you know that this is divisible by 2? Because the units digit is even. So I'm going to keep dividing by 2 until the units digit is not even. So that's the test for divisibility by 2. And we can see that there are 2 to the 4th, there are 4 factors of 2 in the prime factorization of this number. Then you move to the next prime number, 3. How do you know if this number is divisible by 3? Well, the test for divisibility by 3 is to add up all the digits, and if the sum is divisible by 3, then so is the original number. So I can see that these digits add up to 27. 3 goes into 27, so 3 will go into this number. And there it is, 3,468,465. I'm going to try to divide by 3 again. If I add up the digits, I get 36. 3 goes into 36, so 3 will go into this number. And I do that a couple more times, and I see that there's 3 factors of 3, but when I get to here, the digits add up to 32, which is not divisible by 3. So I've so far done 2s and 3s, and I've got 2 to the 4th times 3 to the 3rd is the prime factorization so far. Now I move to 5. Is this number divisible by 5? Yes, because the units digit is either 0 or 5. Of course, we took care of all the zeros by dividing by 2. So we'll only be looking at numbers using this technique where the units digit is 5. 5 goes into here 77,077 times, and that digit, or that number, doesn't end in a 5. So I know I'm done with the 5s. I only had one factor of 5 in the prime factorization. I move to 7. Now, the test for divisibility by 7 is a little bit interesting. So I've come over here and we'll talk about what the test for divisibility by 5 is. It's obvious that 7 goes into this number because I can take 7 into 7 as 1, 1, 0, 1, 1. But the test goes like this. You double the units digit, which is 14, and then subtract that number from the number formed by the remaining digits. So 7707 minus 14 is this. It's not so obvious, so repeat the test. Double this number, 6, subtract it from the digits that remain. 763, still not obvious, so double that digit, subtract from 76, we get 70. If this number is either 0 or a number divisible by 7, then so is the original number. Okay, and here's another example. 11011, double that digit, which is 2. Subtract from 1101, you get 1099. Double that digit, 18. Subtracted from 109 is 91. Double that digit, subtract from 9, you get 7. Yeah, so that number must be divisible by 7, and it is. 1573. Here's a test for 1573. It ends with a 13, so it's not a number. It's not 0, and it's not a number divisible by 7. So we're done with the sevens. And how many factors of 7 were there? 2 of them. And now the test for divisibility by 11, which is the next prime number, is kind of interesting. You start at the right and you add up all the digits that are odd in the odd position. So 3 plus 1 is 4. Whoops, no, I'm on 1573. Add up the 3 and the 5 gives you 8. 7 and the 1 are in the even position. They add up to 8. If you subtract and you get 0 or a number divisible by 11, like 11 or 22, then the original number is divisible by 11. So 11 into 1573 gives me 143. And then here's the test for 143. Add up the odd digits. 1 and 3 is 4. The even digit is 4. Subtract, I get 0. So 11 must go into 143. Whew! When this quotient is a prime number, you're done. As long as you started with the smallest and kept going up the ladder, when that digit is prime, you're done. Okay, so we had 2 11s and 1 factor of 13. So there's the prime factorization for this 166,486,323. Okay, there you go. Hope that helped. If you have any questions, post a comment.